Hello and welcome back. In this lecture, we're going to discuss about ReLU or Rectified Linear Units Activation Function. So this is one of the most popular and one of the best performing activation functions in deep learning, and especially in convolutional networks. So ReLU is very simple. When the input is a positive value, then it's going to stay positive. So there's a linear function. And when the input is negative, then the output is 0. So it's very simply this equation, the maximum between 0 and z. So if your input is positive, then it's going to stay exactly the same value. And if your input is negative, then it's going to be 0. So these are some examples. If your input is 6, then it's going to stay 6. If your input is 0, then it's going to be 0. If your input is negative 3, then it's going to be 0. If your input is 2, then it's going to be 2. So whenever you have a positive value, then it stays the same. Whenever you have a negative value, then it turns to 0. So this is the ReLU activation function, and this is the equation that summarizes the ReLU activation function, the maximum between 0 and z. So z here is your input. Let's say your input is negative 3. So the maximum between 0 and negative 3 is 0. That's why you get 0 here. Let's say your input z is 6. Then the maximum between 0 and 6 is 6, so that's why we have 6 here. Again, let's say that our input is negative 2, so the maximum between 0 and negative 2 is 0, so you have an output of 0. So it's a very simple activation function, which simply is a linear function when the input is positive and is 0 when the input is negative. So in other words, it just converts all the negative values to 0, and thus adding non-linearity. So let's have a look at the derivative of ReLU. So remember, ReLU is basically equal to x when the input is positive and 0 when the input is negative. So the derivative of x is 1. So when you have x as a positive value, then the derivative is 1. Because the derivative of x with respect to x is 1. And when you have a negative value, then it's just 0. So this is a constant. The derivative of a constant is 0. So that's why you have 0 when your input is negative. So the derivative is also very simple. Now, here there's one small problem, is that when the input is negative, the output is 0. And when the output is 0, that means you're going to be multiplying other values in the chain rule with 0. So therefore, the gradient will die when the input is negative. Because once you multiply all the gradients with 1, 0, then basically the result of all the gradients will be 0. The result of the multiplication of all gradients is 0 when there's only 1, 0. So if there's just one negative value, then all of the chain of gradients is basically going to be 0. So this is one disadvantage of ReLU. And here's an example. When initializing from the normal distribution, with a mean of 0 and the standard deviation of 1, then realize that according to the normal distribution, half of the values are negative. Okay, half of the values are negative and half of the values are positive in the normal distribution. So if you activate these with the ReLU activation function, that means you're setting half of the values to 0. So this is one drawback of ReLU. So in order to solve this problem, parametric ReLU was proposed, which is PReLU for short. And basically, what parametric ReLU does is that when the input is negative, the output is not 0, but it's going to be alpha times y, which means it's going to be a very small negative value. And the good thing about it is that this alpha is learnable. So you can learn this alpha. You can learn how much the slope is when you have a negative value. So it's very good to learn the slope because depending on your application, you might need negative values and sometimes you might not need negative values. So if you don't need negative values, then this alpha will be learned to be 0. And if you still need negative values, then this alpha will be learned. So this slope will be learned according to your network and the backpropagation. So this is parametric ReLU. Rather than outputting 0 when you have a negative value, then basically you have this very small negative value, but not 0. So it's very small, but it's not 0. And this slope is going to be learned. So this alpha is going to be learned by the network. Now there's one a special case of parametric ReLU when you set this alpha to a constant of 0.01. So this is going to be called leaky ReLU. So this is the static case. So this alpha here is static. It's a constant. It's not learned. When this is when you set this to a constant value, and especially 0.01, then basically you're using leaky ReLU. Okay. So leaky ReLU is basically going to be 0.01 times x. And parametric ReLU is alpha times x. Parametric ReLU, you learn this alpha, and leaky ReLU, you don't learn this alpha, you just set a constant value of 0.01, and this is called leaky ReLU. And finally, the derivative for the parametric ReLU. So when your input is positive, then again you have a derivative of 1 because it's x. So it's still a linear function here when the input is positive, and the derivative of x is 1. So there's nothing new here. But now when your input is negative, then the derivative is not 0 as we said here, but your derivative is alpha. Because this is the equation that you have. It's alpha times x. Okay, so if you derive alpha times x with respect to x, then you get alpha. So in leaky ReLU, the derivative is 0.01, and in parametric ReLU, it's the derivative is basically this alpha value that the network has learned. So the parametric ReLU solves the ReLU problem, the problem that ReLU suffers from, which is the dead neurons. When it outputs 0 for all the negative values. This problem is called the dying ReLU. Okay, so that's it for ReLU and parametric ReLU. Thank you very much, and I'll see you next time.